Now that you've had a little bit of experience working with proofs, we're going to take a break from that. We're going to concentrate on the logic and study logical operations and truth tables. We're first going to talk about logical operations, tell you what they are, introduce the notations. We're going to show how to summarize these logical operations using truth tables. And then finally, we're going to explore what it means to be a negation and how we find them in actual statements. And we're going to do some examples. So we're going to be looking at something called symbolic logic, and that's all about interpreting logic as a kind of arithmetic operations, sort of like addition and multiplication. And in order to see how that works, I want you to think a little bit more abstractly about what arithmetic is really like. So if we're thinking about what addition is, we can think of it in a really concrete way, combining quantities. But we can also think of it as a way of combining numbers. In other words, what we're kind of doing is taking two numbers, say, 4 and 5, and then we're turning them into one number. And the way we turn them into one number is we add them together, we add the 4 and the 5 together, and turn them into the one number 9. Now, we have very important rules about how we do that, but on a very abstract level, that's all we're doing, taking two numbers, turning them into one number. We are going to do the exact same thing with logical operations. They're going to do the same thing as, say, addition, but they're going to be slightly different quantities. The quantities are not going to be numbers. They're going to be quantities that can have the values true or false. And if that sounds familiar, yeah, we're talking about mathematical statements. Statements are precisely sentences that have a value of true and false, and that means we can do logical operations on them. All right, so we're going to do logical operations. Remember, the quantities we are going to be dealing with, the variables that we use are going to be statements. So our first logical operation is the AND operation, and you've seen this one in action before. Okay, so we're going to use a symbol to denote that operation. That symbol is going to be an upside down V. So if I want to take two statements, say P and Q, and use the AND on them, we're going to put that little AND symbol between the P and the Q. That means we're going to use that operation, and that means P and Q. Now we kind of know how the AND operation works on statements. We've actually used them, right? We know that this is going to be a true statement when P and Q are both true statements. And it's going to be a false statement when one or both of them is false. That's how we use AND logically in our statements. Now, if we wanted to, we could actually summarize this computationally using what's called a truth table. So how does the truth table work? Well, we're going to have three different columns. One for the statement P, one for the statement Q, and then one for the statement P and Q. And what we're going to do is we're going to look at all the possible ways we can have P and Q be true. There are actually 4 different ways we can do that. They both can be true. There are 2 different ways that one of them can be true. And then one way that they both can be false, right? And then what we're going to do is across from that show what the corresponding value of P and Q is. So for instance, when P and Q are both true, P and Q is going to be a true statement. P is a true statement, Q is a true statement, and that means P and Q is a true statement. Now, we can have P be true and Q be false. If that is the case, then P and Q is a false statement, right? Only one of P and Q is true, that means P and Q has to be false. And if P is false and Q is true, again, one of them is false, that means P and Q is also false. And of course, if both P and Q are false, that means P and Q itself is a false statement. And those are the 4 different ways that we can have P and Q be true in combination, and right across from each of those possibilities tells you what the value of P and Q is. So if you had 2 statements and you wanted to know what happens when you take AND of both of them, P and Q, you would figure out what their truth values were, look at how that corresponded in the table, and then look across to see what P and Q is going to be. Alright, so now let's go ahead and do the same thing with OR. Now remember, when we do OR in the context of doing math, we're doing the inclusive OR, which means it's false when both statements are false and true if one or both of them is true. So our symbol that we're going to use is just a regular old V. And so here's how we put that V in between P and Q to indicate P or Q. And then we're going to make a true, and that, remember, that is going to be true when one or more of P and Q is true, and then it's going to be false when both P and Q are false. And we can make a truth table just like we did before. One column for P, one column for Q. Again, we have two variables, which means we're going to have 4 different rows, one for each combination of P and Q being true or false. If they're both true, then P or Q is true. If P is true and Q is false, at least one of them is true, so that means P or Q is still true. If P is false and Q is true, one of them is still true, so P or Q is also true. But if they're both false, then P or Q is false, and that gives us all the possibilities for P and Q. That gives us then all the possibilities for doing the computation P or Q. Now, the logical operations we've looked at so far have been between 2 variables. The not operator is a little bit different in that one only has one quantity that it applies to. So first of all, its symbol is a little hook, I guess you could call it. I don't know, it looks like a hook to me. And if you put it in front of a statement P, that means not P. So not means the opposite truth value of what the statement is. So whatever the truth value of P is, not P is going to be the opposite. So if we're going to make a truth table, first of all, this truth table is only going to have 2 rows. We only have one variable. P can be true or it can be false. So we're only going to have 2 rows instead of 4 like we had before. If P is true, not P is going to be false, because again, the not operator reverses the truth value of our statement. And then if P is false, then not P is true. Pretty straightforward. Okay, so the last operator we're going to look at is the implication or conditional operator. This is going to be an operator between with two quantities, just like and or were. The symbol is going to be an arrow going from left to right. It's going to be P points to Q, and that is going to mean if P then Q, or could also be said P implies Q. And so this is like the conditional statements we were talking about back in chapter 1. If P then Q is going to be false when P is true and Q is false, and then it's going to be true otherwise. And again, we can summarize that in a truth table. We're going to have 4 rows this time since we have 2 quantities that we're looking at. One column for P, one column for Q, one column for P implies Q. If both P and Q are true, then P implies Q is true. If P is Q and true is false, that is when my kids behave, but I didn't give them a cookie. That's false, right? P is false, Q is true. That was when they didn't behave and I did give them a cookie. I was a bad dad, but still not a liar, so that P implies Q is going to be true. And then if P and Q are both false, P implies Q is going to be true. Just like we were talking about with conditional statements. Now we can actually use our truth tables for our operations for more complicated operations, right? So let's say I take P implies Q and then take that statement and that with R. So this is P implies Q and R. Well, this is going to be a little more complicated. First of all, we're going to have a few more rows of our truth table. We're going to have actually 8 possible ways that we can have P, Q, and R be true or false, and also to try to summarize them as we go along. And then so when we do that, here are our 8 rows. The first one is when all 3 are true. The next 3 rows are when one of them is false, R, then Q, then P. The next 3 rows are when 2 of them are false and one of them is true. And then finally, the last one is when 3 of them are false. And then that's the only way. So we got one of them where they're all true, 3 of them where 2 of them are true, 1 is false, 3 where 1 is true and 2 are false, and then 1 where all 3 are false. And then we have I put a column in for P implies Q, because that is kind of the operation that you have to do with just 2 of the variables. It's not quite as complicated. And then once you know P implies Q, you put that together with the R column to find P implies Q and R. So I'm going to first look at the column P and column Q, and then look at P implies Q. Now, P implies Q is false when P is false, Q is true, and then false otherwise. So if I look at where P is true, Q is false, that is going to be on row 3 and row 5. and the rest of them should be true. So notice you have a false on row 3, a false on row 5. All the other rows have true. Now, if I want to look at P implies Q and R, I want to look at the columns for R and for P implies Q. The AND operator is true when both statements are true and false otherwise. If I look at what happens when both statements are true, notice on the first row, both of them are true. Both R and P implies Q, both true. And let's see, 1, 2, 3, row 4 also, both are true. And then 5, 6, row 7 also, both are true. The rest of them, at least one of them is false. And so on rows 1, 4, and 7, you get a true, and then the rest of them you get false. Alright, so before I end this video, I want to make one little comment about negation. And just part of it is negation can be hard. It seems a ridiculously simple operation. If the statement is true, then the negation is false, and if the statement is false, the negation is true. But in applying it in a concrete situation can actually be kind of difficult. So the definition of easy, sometimes applying it can be hard. And let me give you an example. So suppose I have a statement, I am in the kitchen or I am in the living room, and I want to find its negation. I actually want to state its negation, not just look for its truth table, because truth table is pretty easy. But if I want to actually write the negation in a useful way, well, if I want a cheap and correct but not very useful answer, I could just say, it is not true that I am in the kitchen or I am in the living room. Now, while that is perfectly correct in terms of being a negation, it is not particularly helpful in terms of being evaluated. If I saw that statement, I'd have to cross my eyes and stand on my head to try to figure out when it's true and when it's false. But there is a more useful way of doing it. But first, before we do that, we need a model for understanding how negations work. And of course, I have one for you, just in case you want to use it. The negation of a statement could be thought of as a statement that precisely describes what it means for the original statement to be false, which actually kind of makes sense, right? If I describe a situation where the original statement is false, when that original statement is false, the statement I'm saying is going to be true. And as long as I make it so that it doesn't have any other situations outside of that, then when the original statement is true, then my negation is going to be false. So it makes sense in terms of how we originally define it, but it makes it a lot more concrete in terms of being able to say, find the negation of I am in the kitchen or I am in the living room. So the question is, if I'm to describe what it means to be false, well, it's going to be true when one of those is going to be true. So for instance, if I'm in the kitchen, then that statement, the original statement is going to be true. So if that statement has a chance of being false, can't be in the kitchen, right? If I happen to be in the living room, and I don't even care what's going on in the kitchen, if I'm just in the living room, then that original statement is going to be true. So if I want to say what it means for that statement to be false, I can't be in the living room either. So I can't be in the kitchen, because if I were, that statement's going to be true. I can't be in the living room, because if I am, the statement's going to be true again. And both of those things must happen. I can't have one of those things fail. If I'm in the kitchen and not in the living room, it still makes the statement true. If I'm in the living room, not in the kitchen, still makes the statement true. So both of those statements have to be true, which that sounds a little bit familiar. Doesn't that sound like an and statement? So then the negation is going to be I am not in the kitchen and I am not in the living room, which is a much more useful way of stating what it means for that statement, I'm in the kitchen or I'm in the living room, to be false. Alright, so now that you've had a look at what truth tables look like and how to deal with negations, I have two sets of activities for you to look at. One is called truth tables, the other is called negation of a statement. They are both on PDF files included with this video.